Oh man, I've just noticed the last one. 59 minutes and 59 seconds. That's going to irritate me now. Okay, so the recording started again, so we'll move on to the second part. So we're nipping back now to chapter 11, which is implementing file systems. Now, we started talking about file systems last week, and what I wanted to do was do the mass storage stuff first to give you an idea of how we might store things on a device, and that might then impact about how we decide on the file system that we choose and how we do it. Okay, so we'll look at different ways of doing it as we normally do to try and figure out the best way of setting up these file systems that we talked about before. As we go through it, I am under no illusions that the sorts of stuff that we'll be talking about are understandable on the first time through. Much of it is, but some of it you'll need to go back and grab yourselves a bit of paper and just try and work your way through it. So when we talk about multi-level indexes for file storage on a file system, you'll probably want to go back, sketch it out and try and understand how it all fits together. Because if you can understand it first time through, well done. You'll cruise the whole module. I'm not one of them. It takes me a wee bit of time to get it into my head. Okay, so we want to talk about implementing this file structure that's going to be on our mass storage unit. So let's talk about the definitions when we're going through, just so we have a set language that we can talk about things for. And usually when I go through this, I'll start talking about disks because they're most often hard disks, but of course it can be anything. They don't have to be hard disks. So we'll have file systems on these disks, not necessarily a disk, it could be anything. And those file systems need to allow both the user to get access to things and allow the disks to store all the data in a way that's easily accessible and rememberable. He says, making up the word rememberable. There'll be a direct link between the file system and the hard disk, probably, because the amount of data that we'll be storing things in will probably be a multiple of the size of the block on the disk. Now, it's not a one-to-one because you'll have different devices, but it would be kind of silly to have a sector of 333 bytes that doesn't fit into anything. So most of these end up being powers of 2 that fit into one another. So we have blocks of sectors. So we take the stuff that's on the disk, put it into a chunk, create a block. We will also have information about where the files are, and that's in a file control block. We need to have information about the device itself, so there'll be device drivers. So we've got all of these different levels, users, and how the file system thinks of itself and how that's then organized and how that then goes on to a disk and how that disk is then accessed, which means we'll get a whole pile of layers that we get through before we get some data. And you might think that that's overly complicated. And in fact, some operating systems will strip out loads of these things, depending on what they're being used for. But for a general operating system, one that's used for different things, this is really the only way that we can do it. Of course, we have different devices. Look at the machine that you're looking at just now. Even if you're watching this on a phone, you probably have two different storage devices. You've probably got your internal memory and a micro SD card, for example. So you probably get two storage devices, at least. So they, of course, need different I/O control because they're physically different. But we don't want to know about it, so we need some sort of file system that they will both use, and the files on that need to be organized, and we need to have a way of how we think about it, no matter what the device, and one that makes sense to us users rather than people who understand about the internals of an operating system like you guys, because that's how we, through our application programs, will see it. So the file system goes through all these layers in order to access things. And that means that it makes it easy to add on, for example, a USB drive, because that USB drive will live there. It'll have a slightly different I/O control, but everything else up here will all work in the same way, and we won't have to care. We don't care that it's physically different. We don't care that we're accessing a USB drive or a network or a DVD-ROM. It makes no difference to us. We just give us it. But what we're most often talking about is the hard disk that we've just looked at, that's set up in the way that we've just discussed. Okay, so the device drivers will actually physically do the access of disk that we've been talking about, the one where you go to a specific cylinder on the disk, go to a specific sector and read that in. Go to drive 1, cylinder 72, track 2, sector 10, and bring the data that's in there into memory location 1060. Might be the sort of command that you give to the device driver. So it goes to the device, grabs some data, puts it in memory, done. The basic file system will grab the logical block. And remember, that logical block might be made up of multiple sectors. So you might have to give 4 of these commands to get a block. And that data is then held somewhere. So I pointed out when we were looking at the internals of a hard disk that there's a controller. One of the things on a controller will probably be a buffer, some memory, so that the data that you read from the disk can be held in memory until it's ready to go to wherever it requested it. When you think about it, you have to have that. Otherwise, what you'd have to do is synchronize the whole system being ready for some data to be put to a particular piece of memory when the disk was ready. So the whole system has to stop while the disk rotates and the head moves in and out and the data is read and brought in. No. Put some memory in there, call it a buffer, and have it ready when the computer comes back, or when the calling device comes back. So we've got this idea that we've got different things. We've got the physical setup, we've got the logical setup, and we need to have something in between that translates between them. So the logical file system thinks about files the way we think about them, with a name and a creation date and a size and whatever it happens to be. And that's great because different devices might have different logical file systems. We can't impose what our operating system would like on a device. So we might be able to, for example, set up our hard disk to have all the different things. We saw a week or two ago that the Mac operating system can have labels. It can put colors against a file. Well, we can't mandate that, for example, our CD disk has a place on the file to store that label. So it might have a slightly different file system with slightly different metadata. Some things are fairly universal, a file name, for example, but a file color, no. So we have different file systems for different reasons, perhaps because it's a different device, like the CD or the DVD, perhaps because you want to do different things to it, because you're trying to set up a file system to be fairer or to have better access for different types of data. And we talked about that before when we talked about file systems in general. That's why we don't just have one. If we could say, yes, here's the file system and it works great for everything, well, that'd be fantastic. We could take all of our data everywhere we go and everything could read it. But it doesn't work for everything and it can't work for everything. And in fact, there's barely a month goes by without somebody saying, oh, by the way, I've come up with this new idea. So let's get a file system to implement it. I've got two network file systems on my disk. I've got OneDrive and I've got Google Drive. They use different file systems, they use different device drivers, you use different accesses. So we get new things all the time. So how do we start setting these things up? There's some things that we will need on our devices. Again, when we looked at media, we talked about having a boot control block, something that allows us to start up an operating system from that device. We'll have details on the different volumes. So if we've split up our device into different volumes, we'll need to remember that. How many blocks there are, where they start, where they end, what's been used, what's free, so that we can save things onto it. And talking of saving things, we probably just don't want just one big pool of files. We probably want to have some sort of structure on them, some sort of directory structure. So that will need to be stored. And of course, within that, you will have, and again, we've spoken about this before, some data about the file itself, the file control block, storing all the different information about the file that we have. Now that's all on the disk, and it has to stay on the disk because eventually you'll turn off your computer. So it has to be on the disk to remember it the next time you turn it on. But we probably, to speed up things, also want to have some of that in memory. We'll want to have things in memory so that we know where files are, so that we can go and get them. Because otherwise, every time we wanted a file, we would have to go to the directory structure that's stored on the disk, find out where that file is, and then do another access. So at minimum, we're doubling file access times because we have to go back to the device twice. So what we'll tend to do, and the diagram's better than the slide there, what we'll tend to do is bring, say, the directory structure into memory. So when we open a file, we already have the directory structure, we'll know where it is, and that allows us to go to our disk and grab the data, whether we are reading it or writing to it. Whether we're opening it or reading from it. So once we open the file name, so we say open thread.txt, we have a directory structure in memory, and it goes and says, okay, that file's there. Well, now to know that file's there, let's remember that too, so that the file control block can also be brought into memory, so that as we are working our way through that file and reading different bits, we can then go and get that from our secondary storage. So we've got different ways of accessing it, and to speed it up, we bring them in. And that's great if we have the memory. because depending on the size of your disk, depending on the number of disks, depending on the number of storage devices, that might be a lot of directory structures, it might be a lot of file access tables. That's going to be a lot of memory. We also have the idea of partitions, where we split up our devices into multiple logical sections, and they need to be connected to the system somewhere, and that connection is called mounting. And again, we spoke about this last week, this idea that sometimes we don't even notice it. We stick in a USB drive and it just appears as drive G. Well, lucky us. The only time it actually gets upset is when we take it out without telling the operating system we're going to remove it. Because all of these pieces of data that we are saving, file control blocks, directory structures, even the data itself, they have to be updated. Because if we've read them into memory and changed things, we have to write them back out at some point. And if we remove our device without doing that, all of those structures will be out of date and we might lose data. Either because we haven't saved it to the structure or because we haven't saved the pointers to the data in the directory structure or the file control block. So we've got pointers to these partitions. We've got pointers about where they live. Unix, for example, might have one disk for programs, and that's mounted at a place in the file system called /bin for binary for program files. And it might have another disk that stores user data, and that might be mounted at /usr for user. Windows uses letters, Macs use names. It just depends on the operating system. Most devices though will have a root partition, the main one where your operating system is stored. When you start up the computer, and you've probably seen this on your own machine, it says checking file system. So it's going, checking what devices are there, but more than that, it's also checking that the device is consistent. Are all the files that the directory structure is pointing to, are they there? Are they pointing to the right bit? Is everything okay? And if not, you can have an issue. And some of you may have seen these issues when you've started up your machine. Because if it fails that check, you can have all sorts of problems where it will go away and it will start to go through not just a superficial check, but a really detailed check to make sure that all your data is set up properly. All okay so far? Okay, thank you. So we talked about having multiple files. We talked about organizing them into directories. So how are we going to implement that? We could just have a list of directories and point to the directory where it exists on disk. The problem with a linear list, anybody that's done any programming will tell you that searching through a linear list is slow. And it's the sort of thing that we were talking about earlier, Paraskevas, where sometimes we're lucky and it's at the start, sometimes we're really unlucky and it's at the end, but on average, it will take exactly half the time to find something in a list as the list is long. So dead simple to implement, but on average, half the length to access it. So some systems use something called a hash table. I don't know if you've come across hash tables before. And that is a question. I don't know if I need to spend time explaining hashes. Yes, no? Something in the chat, up a hand if you've heard of a hash table.
Yes, I think we came up with this term last year, but like a map, I think.
Yeah, kind of. Okay, so not enough people have come across it. So a hash table is, in essence, a mathematical function. So you point some data at this function and it gives you back a number. The idea is that that number is unique, so that if you point the same data at it, it will always give you that same number. But conversely, if you give it the number, it can give you the data. So it's a very quick way of pointing to some data, because you can, rather than searching through the list, you can point the data to it, create the hash, and that points to a particular place. The trick comes in that function that gives you the hash, because what you want is a set of results that are unique. You don't want to point the same data to it and it comes up with the same number. Sometimes it happens, that's called a collision, and that can cause an issue, but it does speed up getting access to directories. I'll remember and put a link to an explanation of hash tables in the module materials if you want to read more about them. If not, just take my word for it that that's how it works. Next thing we have to think about is how we allocate data on the device. Do we say, right, everything is contiguous? Everything has to stay together on the disk, one block after the other. That's fantastic for performance, because if you want to read a file and that file has 10 blocks, think about how our disk's set up. You can just read block 10, 11, 12, 13, 14, 15, and it's all going, so you just read it as it's going. That's great. But the problem becomes, what happens if that file size changes? Do you leave extra space for it? If not, if the file gets bigger and it's bumped up against something else, do you have to move it to another space on the disk? And do you have another space on the disk that's big enough? And what do you do with that space that's left? What do you put in there? So it's the same kind of arguments that we had 5 or 6 weeks ago when we were talking about fragmentation. Your disk can fragment. And you can have spaces where you can't use things, and you can have lots of space on the disk, but none of them are big enough to actually store what you need. On the other hand, it's really simple to program. Where does the file start? How big is it? Go. Oddly, that's one of the reasons why you might want different partitions in different file systems. What if you had a partition that had the operating system itself? That's not going to change much. The files are going to be there. You're not going to make them bigger or smaller. They'll just exist. So why not have a really simple, really fast, contiguous allocation file system for the operating system, but have a different file system for your data that allows the data to grow? So there's one reason why you might want to partition a disk and use different file systems on it. So for contiguous allocation, for fragmentation, you might have to bring it together, and that's called compaction. But it's really simple. We have a logical file system with one entry, and that points to a physical file system with another entry. This is one of the things I was talking about, by the way, where you might have to go back and look at it. This, I'm not convinced with these types of diagram, but they make more sense when you're reading the book. So I'm not going to spend too much time on them in this lecture. What I want you to do is go back to them later on. And that will help when you're thinking about where things are on the disk. So for this very simple one, it's saying we're looking for a particular block, so a particular part of the file. So we go to position Q, which is the start of the file, and then an offset R. So it's basically saying go to the start of the file and then go this amount into the file to get the bit of data that we need. And for our purposes, in this case, each of these blocks is 512 bytes long. Okay, so that's the general idea with these diagrams. As I say, we've got a few more coming up. I'm not going to spend ages on them because I do think you have to go through in quite a detailed fashion to try and understand what they're doing. So that's the idea. I've spent some time on this one. I won't be spending time on the later ones. I'm more interested in diagrams like this because I think they're easier to see. So what we've got here is how we're thinking about our file. We've got a file called count, and we can store that in our directory saying count starts at 0 and it is too long. And if we go to our physical device, we can see that starting at 0 and for 2 blocks, we have our file count. TR starts at 14 and is 3, so we go to 14. Oh, look, there's TR and it takes 1, 2, 3 blocks. Mail starts at 19 and is 6. 1, 2, 3, 4, 5, 6. Good, it's all working as we expect. Lists the same, F is the same. Okay, so it's contiguous, it starts at a particular place and goes on for a certain number of blocks. So great for unchanging data, less great for files that change. So some systems use still contiguous, but they use something called an extent. They extend the contiguous file. When you ask for a certain, when you ask to create a file, it allocates you an extent, a certain number of blocks. And you can use those blocks. And you're allowed to keep those blocks. And if you use them, that's great. And if you don't, well, that's your problem. It's used quite often in systems. So say think about a big IBM mainframe where you've got lots of different data on it. It makes you think very closely about how much data you're going to have, because you can ask for an extent and you can ask for whatever size that is. But because you are allocated that amount, you're also charged for it. And that might be an internal or an external thing, but you're charged if you want a certain amount of data. So you're very careful to say, well, this is what I'll actually need, rather than just saying, oh yes, give me lots and lots of data. I want to store hundreds and hundreds of things. So it's quite useful in those kinds of things where you have a big system where you want the speed of access, because if you're churning through a huge database, you want to just go and run through it. You don't want to be all over the disk. But on the other hand, you want to have an idea how big your data is so you don't take resources from other places. So you allocate an extent, a contiguous block, and that's then yours. But the file can get bigger, so you can actually ask for another extent and get another block of disks. So it's another set of blocks. So it's another contiguous set. So now your file is in 2 contiguous sets of blocks, which poses a problem, because how do you know that those 2 extents belong to the same file? You're going to have to connect them somehow. So we're going to have to start linking things. So the end of the extent might point to the next extent, or you might have a file somewhere that says, oh no, this file is this extent and this extent. You know, one of the ways that we've looked at before. But it suggests something else as well. If we can allocate a contiguous set of blocks, and then another contiguous set of blocks, and then another contiguous set of blocks, and link them all together, why not just allocate one block and then link that? So rather than saying I need 50 megabytes, say I need a file. And as your file grows and changes, you get allocated extra resources to cope with the size of that file. That's really helpful for resources because you're not using, for example, an extent where you ask for that 50 megabytes, but to start off with, your file is 2 megabytes. So you're wasting 48 megabytes. You've got all that space inside that's not used. You've no fragmentation. So you've no, oh, well, we've deleted this file and there's now a spare set of blocks. Can we fit anything in there? Because everything just points to the next one. So you allocate one at a time. So there's no space, there's no problem. We do have to manage the space because we might still delete files and have blocks become available. So we have to remember where that spare space is. And because we're only getting one at a time, because they're not contiguous, we're back to our problem that we had when we're accessing the disk. The head's all over the place. Not just for different files, but sometimes for the same file. And a badly fragmented file can take a long time to access. Some of you might have come across that. Some of you might have run a defragmentation utility on your own hard disk. And what that does is, in essence, even though you're running a linked system, it grabs all the different blocks that are linked and sticks them all together in one big contiguous block, so that when you're accessing it, things go much more quickly. So, swings and roundabouts. Things might become fragmented, but we don't have to take piles of data at once. On the other hand, every block is connected to the next block, so if something happens in the middle of that block, you're suddenly lost and you don't know where to go next. So reliability can be a problem. But it's a fairly robust system unless you stop the system. So if you just turn it off or don't eject it, and that's why it complains when you just pull out a USB drive, because most USB drives use this kind of system, and it's called a file allocation table. It's been around for 40 years, and that big hard disk that I bought used it. It simply has an allocation table, a table where it says, this is a file and here's the first block. So you go to get that block, and at the end of that block it says, oh, by the way, here's the next block. So you go to get the next block. And that linked list just continues on until you get to the end. There are different variations on that. So you might want to have the whole list to begin with, so you don't have to read the block and get the next one. You might have numbers of blocks that you store, so you might not store everything. You might store the first few so you can get access to them. It just depends. You might also decide to store the pointer not at the end but at the beginning, so that the first thing you read is the pointer to the next block, so you can be ready to go and get it. Something like that. So you get the block and it gets the pointer to your next list, next item in the list. So we have something like this, a file that says it starts at 9. So we go to 9 and we read it, and it's a poor diagram. That's not supposed to say 1 in there, it's supposed to say 16. So that goes to 16, and 16 points to 1, and 1 points to 10, and 10 points to 25, and 25 says -1, which is our notation for saying we're done. And the other thing we've stored in this directory is the end block. So if we get through this, it's worked its way through, we've got to 25 and we've said it's the end and that matches up, then that gives us some comfort. We know that we've got the whole file. File allocation table doesn't bother with the end block, it just has a start block. Same idea, it says go to 217 because that's the first one, and that's got a link to 618, which is a link to 339, and then it stops. But there's no link back. So a file allocation table method can't tell if you haven't got the whole file. Okay, everyone happy with that before we move on to more complicated methods? Okay, well, one of the issues that we have here is speed. So we point to 217. And we have to read 217 to know that we need to go to 618. So we put that in and say, can we get 618, please? And again, we have to then read 618 to know that we also need 339. So we put that into the list and say, can we get 339, please? And then we go and get that. That can take a wee while. And the same issues that we had when we were looking at how we get different blocks when we have a block queue, we could be miles away from it by the time we know that we need to go and get this next block from the disk. So maybe instead of pointing to it from each individual block, we store all the blocks. We have an index that says not just where the first block is, but where all the blocks are. So this time the same file doesn't point to the first block in the data, it points to an index block, and that index block says, okay, well, this file uses blocks 9, 16, 1, 10, and 25. So you can take those and say, please go and give us all of these blocks at once, and that gets the whole file in. Clearly, because you're using a whole block, you may not use all the space that you have for the index block. So all these -1s are just showing you, well, actually, we could store a lot more in here. In essence, it's wasted space, but probably worth it for the speed that it gives us to get to request all of these blocks at once. So that's an indexed way of doing it. So we have an overhead because we've got an index block. And it also brings up a different question. What happens if you use up all of these? Well, there's no reason if we have one index block, we can't have another index block. So this last one, for example, might point to another block that is a second index block to give us the rest of the file, or the next chunk of the file, or whatever it happens to be. So we can start to split up the file into all these blocks. So we can move from single index tables to multiple index tables. So we start pointing at one thing, which points to more than one thing, which points to all the different chunks of the file. So we can have single things. We can have multiple things where we point at multiple blocks at once. We can have multiple things where the blocks that we point to themselves point to more blocks. So depending on the data that we're storing, depending on how complicated we want to make this, depending on how big our files are, depending, everything about this stuff depends. We can implement them. And in fact, there's nothing that says we only have to do one. Unix NFS will do all of these all at one time. So it'll have some things that are direct blocks, so you just point to the data. Some will have single indirect, so you've got an index that points to the data, and some have double or triple indirects, where you point to the data, which points to more indices, which finally point to the data. There's nothing stopping you having any combination that you want. What it will come down to is what's best for your data and what runs the most quickly. Because depending on the file access type you choose, depending on the file system you use, they'll have different consequences for the performance. If you've just got one contiguous file, great, you'll read it really quickly, fantastic. If you've got to read an index file first, that will be a hit. And you can mitigate that hit by bringing the index into memory and using that instead. So there's all of these pros and cons that have to be weighed by whoever's designing the operating system. And in general, run an extra instruction on the CPU rather than doing an extra access to disk. Because as we've said all along, access to disk is far, far slower than just doing an extra instruction. So finally, we want to talk about how we remember not just where things are, but where things are not. How do we know that we can store a new file? How do we know where we can store it? Well, we need to have some free space. We have free space where there's no files, and we need to remember where that is. Now remember how this is set up. We've got logical blocks on the disk, so we could just say there's something in there or there isn't. So we could have a bitmap. 1 bit for every block. If it's 1, then you can use it, and if it's 0, then you can't. And this kind of this thing down the bottom here, CPUs have instructions to return offset within word of first 1 bit. I know that doesn't seem to make sense, particularly if you haven't looked at CPU instruction sets. And I know you've looked at the Little Man Computer, but that has a very restricted instruction set. What it really means is you can throw a piece of data, a word, at this instruction, and it will come back and say the first 1 in this 16 bits is at location 4, which is fantastic if that 1 says, oh right, well that means that our first free space is in location 4. So it's this idea about using a CPU instruction rather than a disk access. Yeah, sorry Harry, I've gone a wee bit long. I've only got 5 slides to go, but I understand if anyone needs to go. I'll finish the lecture. If you can stay, great. If you have to go, I absolutely understand, but the video will be uploaded if you come back to it later. As ever, there's a downside. If you've got a bitmap with every block on the disk and 1 bit for that, then you need some extra memory. And you can work it out, because you can work out, given the size of the block and the size of the disk, how many bits you'll need, and therefore how much memory you'll need. And there's an example on there. A 1 terabyte disk might take 64 megabytes of memory. And that's quite a chunk out of your working memory. So maybe you, rather than storing everything, have a linked list. So the same way as we link the files and point to the next one, maybe we simply have a linked list of free blocks as well. All we need to store is the first free block and how many free blocks there are. And if we want some space, we can just go to that first free block and say, yep, we'll have that one, and that'll tell us where the next one is. and where the next one is, and where the next one is, and so on. And all we then have to update, if that one took 3 blocks, for example, all we would have to do is update the free space list head, which wouldn't be 2, it would be 5, and the amount of free space we have, which would be reduced by 3 blocks. Maybe we could do something else. Maybe we could start to group these things. Because again, we'll have the same issue. We have to go to block 2 to find out that the next one is block 3, to find out the next one's block 4, and so on. Maybe instead of just storing the next one, what we could say is, well, I'm at block 2 and I have 4 free blocks. So we can group them and say, yeah, I've got 4 blocks here, all contiguous on disk. And the next one is at 8. And it says, yeah, I've got 6 free blocks. And the next one's at 17, which says I've got 2, and so on and so on. So maybe we could group our pointers to understand not just where the free space is, but how large it is in one contiguous block. And we could probably extend that to say, well, I've got a file, and rather than using a block of 4 and then the first block of a block of 6, maybe we just use this one and we get the file to be contiguous because it's 5 blocks. We have all sorts of options that we can implement, and we've got that choice. Again, to try and speed up our file access system and to speed up everything that we are doing. Once you start to get to really large storage systems, that becomes very difficult. And I'm talking about hundreds of terabytes here. We certainly can't store anything in memory. We're going to have to store it on disk. But maybe what we can do is divide the space into, in this particular case, they've called it meta slabs. Same kind of idea, you use a space map, but you have lots of them instead of one for the whole system. And ZFS, Z file system, uses this. Whatever we do, we can work out what's more efficient, what gives us the best performance by figuring out how long it takes us to access directories and files and access things on disk and all that kind of stuff. And all of the stuff that we have looked at up to now, how we allocate files on the disk, how we figure out where free space is, how we then allocate that and change that. All of those things will go into improving the performance. As will some of the things that we touched on, things like having a buffer. We can use the same sort of stuff that we do with memory. We've talked before about saying, well, if we access memory location 2, why don't we just get memory location 3, 4, and 5? Because the chances are that's what we'll be getting next anyway. Well, why don't we do the same with file systems? Particularly if we have contiguous file systems. If we are asked to get block 10, well, the chances are we're probably going to need to get blocks 11, 12, 13, 14, 15, 16, and 17, and 18 as well. And if we've got enough space in the buffer on our address, instead of just saying get 10, get 8 blocks. So have a cache. So that the next time it comes back and go, aha, I'm ahead of you, that's already in my cache. There's a cost involved because you need memory chips on your device, but that might be worth it to speed up your access. You can do all of these kind of things. You can try and get ahead of yourself to try and get stuff in when it's happened. You can delay writing out to files. whilst you're doing lots of reads, so that you're not slowing down other things. And then when all the reads are finished, you do all your writes all at once, all bunched together. And that can be an issue if you turn things off or pull your USB stick out. You can do all of these things to try and increase your efficiency. So a mere 11 minutes late, that's that one finished. Does anyone have any questions? Okay, I'll stop the recording then.